Hello everybody, welcome to this video covering the first part of 11.10 Taylor and Maclaurin series. So up to now, the strategy for finding series representations for functions has been kind of ad hoc. We kind of make it up as we go along. The starting point was 1 over 1 minus x is the sum of x to the n, and then we try to use algebra techniques, maybe replacing x by something else or multiplying, or we differentiate both sides, or we integrate both sides to find power series for more functions. But it was never very clear what path we're supposed to follow, or if there even is a path to find a representation for the function we're interested in. And definitely this kind of method would not work for something like finding a representation for either the x or sine x or cosine x. So it's nice to have a more systematic way, and it turns out there is a way to do it, and that's Taylor and Maclaurin series. So let's get started. So the question we're addressing is, if we have a function, can we write it as a power series? And if so, how do we do that? So let's start with the how do we do that question, which is easier. So let's suppose we have a function which can be written as a power series. And so we can write f of x is c0 plus c1 x minus a plus c2 x minus a squared and so on with some coefficients. So here we're assuming the center is a. And the question we're going to start off by answering is, what are the coefficients c0, c1, c2 supposed to be? And then after we figure out what the series should be, we'll talk about later whether a function has a power series representation at all. So, okay, so let's suppose we start with this power series representation. How do we find the coefficients? Well, first thing we could do, for instance, is plug in different values of x and see what we get, because this is supposed to work for all x with absolute value x minus a less than r. So if we plug in x equals a, then we get the equation. On the left side, we get f of a. On the right side, all the terms including x minus a will cancel because they'll go to 0, and we're just going to be left with c0. So we get f of a equals c0, or if you turn it around, c0 equals f of a. So if the function starts with the power series representation, then necessarily the coefficient c0 has to be equal to the function value f of a. So that's at least one piece of information. And then let's keep going. So at each step, we're going to differentiate and then plug in. So let's differentiate both sides of this equation for f of x. We are going to get, okay, c0 is a constant, it goes to 0. Remember we said that we can differentiate power series term by term. So c0 is a constant, goes to 0. c1 x minus a, the derivative of x minus a is 1. So we're just left with 1 times c1. And then we have 2c2 x minus a, 3c3 x minus a squared, and so on. So we just differentiated each term by term to get f prime of x. And then we plug in x equals a. On the left side, we have f prime of a. On the right side, everything still involving an x minus a goes to 0. We're just left with f prime of a equals c1. Or in other words, c1 is equal to f prime of a. So that now told us what c1 is. So let's differentiate again both sides of our equation for f of x, for f prime of x. We get the second derivative of f is equal to, okay, c1 is a constant, it goes to 0. We have 2c2, and then the derivative of x minus a is 1, so we get 2c2. Then we have 3c3, and the derivative of x minus a squared is 2 times x minus a. So we're going to have 3c3 times 2. We get 6c3 x minus a. And then, of course, all the other terms get differentiated, but we're not writing those down right now, but they're still there. If we plug in x equals a, then we're going to get f double prime of a. So the second derivative at a is equal to 2c2, and then all of the other terms, including the ones we didn't write, go to 0. So the second derivative at a is 2c2, or if we would divide both sides by 2, we would get c2 is a half f double prime of a. Okay, we differentiate one more time. We get 2c2 is a constant, it goes to 0. We get 6c3 times 1, so we're just left with 6c3. And then we have a bunch of terms including x minus a. We plug in x equals a, we get the third derivative at a is equal to 6c3. Okay, or we could divide both sides by 6. We'll get c3 is equal to 1 over 6 times the third derivative at a. So looking at what we've done so far, we've managed to compute c0, c1, c2, c3, just by differentiating and plugging in each time. And if you keep doing this, maybe write out a couple more terms, it will be clear what the pattern is. So in general, each time we differentiate, we multiply by a power, we bring a power down, and we keep multiplying them. It turns out that the nth derivative at a is equal to n factorial times cn. So that definitely agrees with what we had so far, and you could check the pattern works. So if we divide both sides by n factorial, we get the cn is equal to fn of a divided by n factorial. Okay, so what have we accomplished here? We've showed that if a function has a power series centered at a, okay, we're assuming that for the moment. So if we have a power series centered at a, then the coefficient cn has to be fn of a divided by n factorial. So we can calculate the coefficients from the function. Okay, so these kind of series that have these coefficients are very important. They appear in lots of places, so they have a name. It's called the Taylor series of f at a with center a. So that's the sum of fn of a over n factorial times x minus a to the n. So we're going to be interested in computing these and studying them. If a equals 0, this is also called the Maclaurin series. So they're sufficiently important when a equals 0 that they get a special name, which is Maclaurin series. Okay, and what if we just want to recast what we proved on the previous slide or what we showed? So we showed that if we have a power series representation with some positive radius of convergence, then by differentiating and plugging in, we show that that power series must be equal to the Taylor series with center A. So we didn't necessarily show that every function is equal to its Taylor series, but at least we showed that if it is equal to a power series, then that series has to be the Taylor series. And now the advantage of studying Taylor series is that rather than with 1 over 1 minus x, we kind of, we had a very indirect method. Now it's very clear. As soon as we know that a function is given by a power series, it's this series. We can compute the derivatives, plug in a, we get some numbers, and we can actually compute this series. So it's a bit more systematic. So let's see an example. So let's take maybe the simplest function for differentiating or for calculus, which is e to the x. Let's find the Maclaurin series of e to the x and the radius of convergence. So all it means to find the Maclaurin series is going to be to go back to the formula in the previous slide with a equals 0. So that's the sum of fn of 0 over n factorial times x to the n. And the unknown here is just fn of 0. This is the thing we have to calculate and then plug into our equation. X to the n is there because it's a power series. It depends on x. N factorial depends on the index of the sum. It's not something we have to find. So we just have to find fn of 0. F of x is e to the x. Okay, fortunately, this is a very simple function. It stays the same as we differentiate. So that wouldn't necessarily be true in general for different types of functions, but for e to the x, it's as good as it gets. The nth derivative is just e to the x. If we differentiate once, we get e to the x. If we differentiate twice, we get e to the x. However many times, we're just left with e to the x. And so after we differentiate, we plug in 0. We get fn of 0 is e to the power of 0. Of course, anything to the power of 0 is 1. So we have fn of 0 equals 1. And now we just go ahead and plug that in the general series for Maclaurin series. So we plug that in our equation. We're left with the sum of x to the n. So 1 over n factorial times x to the n. Or if I multiply across the top, x to the n over n factorial. So this is well-known. It's the Maclaurin series for e to the x. So we're going to keep seeing this. Okay, next step was the radius of convergence. Okay, now we have a power series. So we're going to test the radius of convergence just like we've been doing in the last section. So we use the ratio test and figure out when that's less than 1. So an is x to the n over n factorial. We work out an plus 1 divided by an. Okay, so we're going to get an extra x on the top, so we're left with absolute value x. The an plus 1 term is going to have 1 over n plus 1 factorial. The an term is going to have n factorial. If we cancel those, we're going to be left with 1 over n plus 1. Okay, it turns out that this goes to 0 for every x. So since an plus 1 over an in absolute value goes to 0 for every x, this is less than 1 for every x, so the series converges for every x. Okay, so the radius of convergence is equal to infinity. Okay, so we managed to show that the Maclaurin series of e to the x is the sum of x to the n over n factorial, and the radius of convergence is infinity in this case. Okay, but the problem here is, again, as we said before, we've showed that if e to the x, or if a function is given by a series, then that series has to be the Maclaurin series. Or in particular here, if e to the x can be written as a power series, then that power series is the sum of x to the n over n factorial. We haven't actually shown in the first place that we can write the function as a power series. So how do we do that? And surprise, surprise, we have to look at remainders. So let's start with a function f. If we have a function f, let's write it in this way. Tn of x is just the Taylor series, but only adding up to the nth term. So here, everything is the same as in the Taylor series, but we only add up to the nth term. And then Rn of x is the difference between the function and this kind of partial Taylor series or nth degree Taylor series. And what we want, if our Taylor series is going to converge to the function, we need the difference between the partial Taylor series and the function to be going to 0. So in other words, we need this remainder to be going to 0. So, and this is exactly what we're going to ask for. So if this remainder goes to 0, where this is the difference between the function value and the partial Taylor series, if this remainder goes to 0, then f is equal to its Taylor series on this interval x minus a less than r. So how on earth do we show that this remainder goes to 0? Okay, just like before with alternating series and the integral test, there's going to be an inequality that we can use to bound this remainder, because it's not something we can easily calculate explicitly. Right, we have the function, we have the nth degree Taylor polynomial, but there is no way to easily bound the difference between the two. So we need some kind of inequality. So here is Taylor's inequality. So what does it say? It says that if we want to bound the nth remainder, Rn of x, remember that's the thing we're trying to show that it's going to 0. So we want to try to show it's bounded by something going to 0. If the n plus first derivative of our function is bounded by m on some interval, then it gives us a bound for the for the nth remainder Rn of x. It says that this is less than m over n plus 1 factorial times the absolute value of x minus a to the n plus 1 on the same interval. So here, the main thing that we have to come up with is once we fix our interval, we have to fix this upper bound capital M for the size of the n plus first derivative. This will just depend on what the function looks like. So once we come up with that upper bound, we can just plug everything in the right side and we come up with an upper bound for the remainder. So let's see how to do that, going back to our simplest case of e to the x. So we're going to try to show that e to the x is equal to its Maclaurin series for every x. So remember, that means we have to show that the remainder is going to 0. So let's fix an interval, absolute value x minus a less than d, and try to show that the function is equal to the Maclaurin series in that interval, or in other words, to show that the remainder goes to 0. If we want to do that, we have to use Taylor's inequality in order to show the remainder goes to 0. So we're going to want to start by bounding the n plus first derivative at x. So since the derivative of e to the x is always just e to the x, we're in good shape because the n plus first derivative then is just going to be e to the x. Then we want to bound the n plus first derivative, or in other words, we want to bound e to the x, where absolute value x is less than or equal to d. So here the a is 0 because we're doing the Maclaurin series, the center is 0. So absolute value x less than d, that means that x is between negative d and positive d. So we have to bound e to the x between negative d and positive d. And remember that e to the x is a positive function, is an increasing function. So it's going up. So the largest possible value would be at the right endpoint, which is d. So the largest possible value of the function here is e to the d. Okay, so we've managed to come up with an upper bound for the n plus first derivative on our interval. It's e to the d. So this is going to be our capital M. And then we just go ahead and plug everything into Taylor's inequality. So we have our capital M. We're looking at absolute value x less than or equal to d. We should come up with an inequality for the remainder just by plugging in. Okay, so m becomes e to the d. n plus 1 factorial just stays. Absolute value x, because a equals 0. Here is the inequality we get from Taylor's inequality. So the absolute value of Rn of x is less than or equal to e to the d of n plus 1 factorial times absolute value x to the n plus 1 for absolute value x less than or equal to d. And now we want to show the remainder goes to 0 as n goes to infinity. So we're going to want to look at the right side of this as n goes to infinity. E to the d does not depend on n, so we want to compare the pieces that are depending on n. We have absolute value of x to the n plus 1 divided by n plus 1 factorial. That means we have some kind of power on the top and we have a factorial on the bottom. So you have to question which wins out. Okay, factorials grow more quickly than powers. So in this case, Rn, the remainder is going to go to 0 because the top is going to infinity much more quickly than the bottom, the factorial, is going to infinity much more quickly than the top, which is just a power. Okay, so the remainder goes to 0 for absolute value x less than or equal to d. So since the remainder is going to 0, that says that the function is equal to its Maclaurin series for absolute value x less than or equal to d. Right? That was the whole point of showing the remainder goes to 0. It shows the function is equal to its Maclaurin or its Taylor series. And here d didn't really play any role. It was just a kind of intermediate step in order to let us bound the remainder. So now we've managed to show that e to the x is equal to its Maclaurin series for between minus d and d for every d. So it must also be true for every x. Right, if something is true from negative 10 to 10, and it's true from negative 100 to 100, true from negative 1000 to 1000, then it will be true also for every x. Okay, so we managed to show that the function e to the x that we know and love, that we've worked with so often throughout calculus, it's actually equal to this power series, the sum of x to the n of n factorial. And they're true for every x, so one is just as good as the other. They are the same thing to all intents and purposes. And sometimes it can be useful to have different definitions or different ways of thinking about the same function, because different ways of thinking about it are going to have their pros and cons. Like if we want to do calculus with e to the x, or if we have something like e to the x squared, then the power series is actually pretty flexible, which we'll see. Okay, so this was one example of showing that a function. So we have two separate steps. One is computing the Maclaurin series and the Taylor series of a function, and we're probably going to do that in quite a lot of examples. So if there is a power series representation, it has to be the Taylor or Maclaurin series. Now we've seen how to do that. And then the other step is actually showing that a function is equal to a power series or is equal to its Taylor or Maclaurin series. And to do that, we have to show this remainder goes to 0 using Taylor's inequality. Okay, and we could repeat these steps with various different types of functions, so sine x and cosine x. So if you just work out the derivatives of sine and the derivatives of cosine, they're going to alternate between 0, 1, and -1, and so on. We could maybe do one of those in class. But we can come up with the Maclaurin series that are here on the right. So sine x, the Maclaurin series is the sum of -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Cosine x, it's the sum of -1 to the n, x to the 2n over 2n factorial. So the sine is the even ones, sine is the odd ones rather, and cosine are the even ones, x to the 2n plus 1 and x to the 2n. And so the steps will be the same. We're computing the Maclaurin series, and then we have to show the remainder goes to 0 in each case. And these are valid for every x. So in this case, the radius of convergence is infinity. So sine x is just as good as its power series, cosine x is just as good as power series. These are great representations for the functions. Okay, and just like before in the previous section, we started off with 1 over 1 minus x is the sum of x to the n. And we use that to calculate series for other functions, maybe by doing some algebra or differentiating both sides or integrating both sides. Here we could do exactly the same thing, but starting with these series. So for instance, we know e to the x, so we could also find a representation for e to the x squared, just replacing everywhere the x by x squared. So if we were to do that, we would get e to the power of x squared is the sum of x squared all to the power of n, which is going to be x to the power of 2n divided by n factorial. And this would still be true for every x because it was true for every x before. So you could do this, or you could multiply both sides by x or x squared or so on. So you could use these to generate also more power series than we started with. And this can be useful, for instance, as I've probably said before, e to the negative x squared is related to normal distribution, which comes up a lot in probability of statistics. So it's something you want to be able to compute and understand. So there is motivation there. Okay, and then finally, a couple more power series. So some that we've already seen before, but I think these power series are all worth memorizing, or at the very least putting on your formula sheet. So here let me kind of round out the list. So these ones are slightly less important than before, but still important. So 1 over 1 minus x, we should already have memorized. It's the sum of x to the n. And then we had a couple of variants that we got from 1 over 1 minus x. So for instance, when we replaced x by minus x squared, we got 1 over 1 plus x squared, and then we integrated both sides. We got a power series for arctan x, or inverse tangent of x, which was what we have here on the right-hand side. If you replace x by negative x, you get 1 over 1 plus x, and then you integrate both sides, we can get a power series for ln of 1 plus x. So the second and third ones here are pretty easily recoverable from 1 over 1 minus x. And then harder, but it's probably less likely to be assessed, but I can't rule it out for sure, is 1 plus x to the k. So here, if k is 0 or 1 or 2 or any kind of positive integer, you can just kind of brute force this by multiplying it out, right? So 1 plus x to the squared, you write 1 plus x and 1 plus x, and you multiply out all the terms. Or 1 plus x cubed, you have 3 copies of 1 plus x, you write it out and you multiply out all the terms. But if k would be a half, for instance, so the square root of 1 plus x, there is no nice way to write that out with finite limited terms. Or if k is any positive number that's not a whole number, there is no nice finite representation of this, but it is possible to write it out as an infinite series. So this is the sum from n equals 0 to infinity of this thing k choose n, x to the n, where k choose n has this particular formula. So you can actually calculate the coefficients here. So I think this is worth putting on a formula sheet, but definitely know the 3 from the previous slide and 1 over 1 minus x to go into the xn. Okay, and these ones are true for absolute value x less than 1, so the remainder is equal to, the radius of convergence is equal to 1. Okay, summarizing for this video, we managed to show that if a function is given by a power series, then the power series has to be the Taylor series, or if the center is 0, it's the Maclaurin series. Then there is a separate question of, is a function given by a Taylor or Maclaurin series? Then in that case, we have to show this remainder goes to 0, and one way to show the remainder goes to 0 was by using Taylor's inequality. And then we studied various types of functions that have come up a lot, e to the x, sine x, cosine x, 1 over 1 minus x, and so on. We saw that all of those are represented by a power series, and we saw what the power series was. Okay, thanks everyone. See you next time.